now. Welcome everyone to this new edition of the High Energy Astrophysics Division at the CFA. I'm very happy to introduce our first speaker today, who is Caroline Huang. She's been a postdoc at CFA since September 2020 and currently supervised by Randall Smith and she works on symbiotic binaries with Margarita Karowska, John Raymond, and Warren Heck. She was previously undergrad at Harvard University and graduated in physics and astronomy. She was then a graduate student at Johns Hopkins University and received a PhD in astrophysics under the supervision of Professor Adam Rees, working on distant measures in cosmology. And she's going to talk about to us today the Myra variables as cosmological distance indicators. So please, Caroline, take it away.
Okay, hi everyone. Let me share my screen. Okay, can everyone see my slides? Okay, great. So today, as Federico said, I'm going to be talking about Myra variables as cosmological distance indicators. This is work I did during my PhD, and some of it is still ongoing. So even though this is a higher energy seminar, I thought this might be relevant. And I'll finish up with a little bit about some of the current work I've done with Margarita, John Raymond, Margarita Karowska, John Raymond, Warren Hack. Okay, so just a brief introduction into why we care about distance indicators. As many of you probably already know, there's currently an issue in cosmology known as the Hubble Constant tension. And this is basically the fact that if we look at early universe measurements of the Hubble constant derived from the CMB and assuming a lambda CDM cosmology, we have one number for the Hubble constant that's around 67 kilometers per second per megaparsec. And if we look at late universe measurements of the Hubble constant, as in direct measurements obtained from distance indicators such as Cepheids, TRGB, Myras, or gravitational lenses, we end up with another number that tends to hover around 73 kilometers per second per megaparsec. And as the precision of these two numbers has increased, we've actually found that the discrepancy between them has grown, which raises an interesting question. Is there something that we don't understand in early universe physics that causes these numbers to not match each other? Or is there perhaps some problem with our late universe direct measurements of the expansion rate? And so what I'll be focusing on is this work right here, the Myra value of the Hubble constant, which was the core of my PhD thesis. And one of the reasons we're particularly interested in measuring the Hubble constant with new independent calibrators is that it can help us address this question. If we can improve the measurements of the Myra Hubble constant, as you can see right now, the uncertainty is very large. Maybe we'll be able to understand if the Cepheid measurement is reliable, or if it turns out that the Hubble constant is more in agreement with what we get from early universe measurements. So just a quick overview of how this works. The most precise measurement of H0, or the Hubble constant, comes from the Cepheid supernova distance ladder. And it basically has three rungs. And the first rung is where we use geometric measures of distance, so parallax or megamasers, to measure the distance of Cepheids in the nearby universe. So a Cepheid is a massive star, but it's still a star. And so even though it's rare, we can detect them close enough for us to get geometric measures of their distance. And then they also follow what's called a period luminosity relation, meaning that their period and their luminosity is correlated. So if you see a Cepheid of a certain period, and you automatically know what the luminosity is. So with the geometry, we can put an anchor. We can actually figure out the luminosity of the Cepheid. And then from there, we can search for Cepheids in a farther away galaxy that's host to a type 1a supernova, which is a different type of standard candle. A type 1a supernova has a fixed luminosity. So if we see how bright it is, we know how far away it is. And then once we've used the Cepheids to get the distances to the type 1a supernovae, which are much farther away, they are also much brighter. And type 1a supernovae directly in the Hubble flow, where galaxies are moving as a result of the expansion of the universe and not by local gravitational interactions, can allow us to figure out the Hubble constant. And so this is actually a really crazy process because if you look at Reese et al. 2016, which is at the time the most precise measurement of the Hubble constant, there are actually 4 different anchors. So here we have the Milky Way, LMC, M21, and NGC 4058. Those are the galaxies where you get the geometric distances, but they span themselves 23 magnitudes with less than 2% error in order to get this measurement. So what is a Myra? So I mentioned briefly that a Cepheid is a variable star that's massive. A Myra is also a variable star, and it can play the role that Cepheids play in the distance ladder. But unlike Cepheids, they're not necessarily massive stars. They're located at the tip of the asymptotic giant branch, and they have periodic variability. So actually this is, they're very interesting because they're highly evolved, and so they're not even necessarily spherical. This is a picture that was taken using Hubble Space Telescope by Margarita Karowska, whom I work with at the CFA, and you can see that there's these large convection cells that give it a weird lumpy shape. And they also have long periods and high variability. So the periods can range from 100 to 1,000 days, and the variability can be up to 10 magnitudes in the visible. And so Myras actually have the largest amplitudes of periodic variable stars. And like Cepheids, they follow a period luminosity relation in the near infrared. So here's a diagram of all of, well, not all, but many of the variable stars. And you can see their amplitude and their period. But for distance, we focus primarily on Myras of less than 400 days. And the reason for this is because Myras at less than 400 days tend to be oxygen rich, and oxygen rich Myras tend to follow a cleaner period luminosity relation. And these objects are comparable in luminosity to Cepheids, but unlike Cepheids, they're ubiquitous, meaning that because they're not massive, we can detect them everywhere, and we can detect them in near infrared. That allows us to look at galaxies without star-forming regions, which we have to do for Cepheids. And it allows us to take advantage of the next generation of space telescopes, which will be primarily focused on the near infrared. Cepheids can't be detected in the near infrared because they have low amplitude variability in the near infrared. So they're typically detected in the optical and followed up in the near infrared. But with Myras, we can, as you will see, use only near infrared data to classify them. So for the Myra distance ladder, we have 2 anchors, and the first one is the LMC. And the LMC has a detached, the Large Magellanic Cloud. It has a detached eclipsing binary distance that is precise to 1%. And here I have some period luminosity relations for Myras in the LMC. And there's 2 types of Myras, one that are oxygen rich and another that are carbon rich. And the oxygen rich Myras in blue, as you can see, follow a period luminosity relation that's quite tight. But the carbon-rich Myras don't tend to follow this period luminosity relation. So they're the red blob there. So basically, we want to remove carbon-rich Myras when we're studying these objects. The second anchor for our distance ladder is NGC 4258. So this is host to a water megamaser, and it has a geometric distance of about 1.5% precision. So this is work that I did during my PhD, where we looked at NGC 4258 at one part of the galaxy, and we discovered Myras there and created selection criteria for separating the oxygen and carbon-rich Myras from each other. And one of the objects in our sample, you can see in the upper right-hand corner, there's these timestamps of our observations which spanned about a year, and you can actually see it growing brighter and fainter. So we also created period luminosity relation for the Myras in this galaxy, and we use this to calibrate the luminosity of the Myras that we will study in type 1a supernova hosts. So just a sanity check, since we've been talking about how Myras are not young stars and Cepheids are, do their distributions match this? And the answer is yes. So when we look at 4258, we can see that the Cepheids tend to follow the distribution that mirrors like the star-forming regions of the galaxy, whereas the Myras, they tend to be distributed evenly across our observations. So we have here are the ACS observations of this field, and then on top of it are the HST WIF-C3 observations in the near-infrared, which has a smaller field of view. And since it was taken over the course of the year, the orientation angle also rotated. So that's good. Okay, so in this galaxy, since it had been extensively studied due to the water maser, we also had some optical data. And this was very useful because Myras had been studied primarily in the near-infrared only on the ground. And they're actually easier to separate between the two types in the optical. So we wanted to look at whether or not using more optical data would get us a different or better PL relation than using only near-infrared data. So we created 3 samples, one which we called the gold, which used the most selection criteria, then the silver, then the bronze. And the silver and gold both involve optical data. But what we found in the end was that whether or not we used optical data didn't really change the 0 point of the PL relation. And what this indicates to us is that we don't need the optical data in order to create a clean Myra PL, or at least one that has a consistent 0 point. So that's very good because that means we don't have to get optical and near-infrared observations of the same galaxy. So the second part is rung number 2, which is then tackling galaxies that are host to type 1a supernovae. So also during my thesis, we looked at NGC 1559, which was the host of SN1A 2005 DF. So this will eventually have a Cepheid distance as well, but we got 10 epochs of F160W, which is the H band for HST, with a baseline of about 370 days. And this is the first of 4 type 1a supernova host galaxies targeted by the SHOES program that is also going to be looking for Myras in those other galaxies. So here again, we found that the best selection criteria were as similar to NGC 4258 as possible to keep things consistent, but we included this time because it was farther away and the observations were noisier, a statistic of how certain we were that it was a variable object. And then we also excluded all the objects from the high surface brightness regions of this galaxy. So in this lower left-hand corner, you can see the galaxy and the locations of all the Myras in red. This is because we want to reduce the effect of crowding, which is where we have too many objects with PSFs too close to each other to really separate. And that might artificially increase the brightness of the objects we're detecting and therefore bias the PL relation. So we did a careful accounting of all of our systematics and statistical uncertainties in this situation. And we found that the systematic uncertainty is dominated by the differential extinction between 4258, which is our anchor, and the type 1a supernova host galaxies. But overall, our uncertainty in the Hubble constant measurement is dominated by the type 1a supernova peak magnitude. What I mean by that is that even though type 1a supernovae are standard candles, there's still some variation in their luminosity. And because we only have one type 1a supernova that's been calibrated by a Myra distance in this project, that is still the dominant source of uncertainty, the random error on that. So the end result is that we got a best value of 73.3, which is in agreement with the Cepheid results. And this is also a 5.5 measurement of the Hubble constant. So this is actually good because since these results are dominated by the random error, if we then go and look at other type 1a supernova hosts and measure distances for other type 1a supernovae, this number should go down as approximately 1 over square root of n, where n is the number of supernovae that we're calibrating. So where does that lead us in future work? So there's a few areas that we want to tackle, and the first is decreasing this uncertainty. So obviously, the best way to do this is to observe more type 1a supernova galaxies. So SHOES has also obtained near-infrared time series observations of 3 other SN1A hosts, which will be used to search for Myra variables and Cepheids alike. And there was another cycle 28 proposal from the group, which will obtain some additional orbits, and that will allow us to get some near-infrared colors and to have a longer baseline in these galaxies. And one of these galaxies actually has 2 supernovae, so it's like a bonus. And And then in addition, I'm also going to be working on, like over the next year as well, studying SN 2001 FE, which is a supernova located in the galaxy M101. And it's actually the nearest type 1a supernova in decades. And for that reason, there's actually a host of archival observations for this supernova, in which people studied the supernova field in order to study the late time light curve of the supernova. And because Myras are old stars, I can actually use these observations myself to look for Myras in this region and then derive period luminosity for the Myras using the archival data. However, because the archival data alone is not quite enough to get us the uncertainties that we would like with this distance measurement, I also have a cycle 29 observing proposal, which we're going to get some follow-up observations of this field, both to increase the footprint, therefore allowing us to get more Myras, and also to increase the baseline, which would allow us to study long period Myras in this field. So long period Myras, as I mentioned earlier, we typically exclude because many of them are carbon rich, but they're also much brighter, and they could potentially allow us to measure a Hubble constant even without type 1a supernovae if we can find a way to separate the oxygen rich and the carbon rich Myras from each other. So that's another thing we're interested in, and this proposal will kind of allow us to do a little bit of both. And that's what I'm going to be working on over the next year as well. So in summary, increasing precision in independent measurements of the Hubble constant are needed to understand this tension. Myras are a possible independent calibrator of type 1a supernovae that will benefit from future infrared and near-infrared missions. And with these additional observations, we'll have a total, they're not completed yet because each set of observations needs to take more than a year. We'll have a total of 6 local type 1a supernovae in the next couple of years, and that'll bring the uncertainty down from 5.5% to 3%. So on this project, I was collaborating with Adam Rees, Wenlong Yuan, Nadia Zakomska, Stefano Casartano, Patricia Whitelock, and Lucas Macri. And so since this is a higher energy seminar, I just wanted to talk a little bit about some of the work I've been doing with some of the people in the higher energy division here, particularly Margarita Carrasco and John Raymond. And we had been studying, and also one Hackett Space Telescope. So we've been studying the system of our query, which is one of the nearest symbiotic systems. So it's located about 220 parsecs away. And it's also the nearest stellar jet, which is really exciting because it allows us to study jet formation at regions very close to the start of the jet. And this system consists of a Myra variable with a period of about 387 days and a white dwarf. And they have a period together of 44 years around the center of mass. So the brightness changes for this system are actually visible with the naked eye because of the Myra. And we also see these beautiful large scale features that include a northeast southwest jet, which you can see here, and a nebular region that was probably the result of novas in the past. And the jet itself has been observed at wavelengths ranging from X-ray to radio, but we're going to refocus on the UV and the optical. And specifically, we're going to focus on this region here, which is the inner jet. So this is a Hubble image that was put together by Judy Schmidt. And we basically have observations that were taken in 6 emission line regions, Mg2, O2, O3, H alpha, and sulfur 2. And we used 3 continuum bands to subtract the continuum as well. And we obtained 4 dithers for each exposure. So we use that to drizzle subpixelated and nominal resolution images. The tricky part about this was the alignment, because we only have one pseudo point source, which is the Myra. The Myra itself is not a point source because, as you saw earlier, Myras are resolvable by HST. Oh, 2 minutes, thank you. And we also, from this, obtained proper motion velocities for several knots that were visible in the system using a comparison of 2017 and 2020 observations. And then on top of this, we selected some regions of interest using data Margarita has from X-ray and using the UV and optical morphology. So these are the regions highlighted here. And we also obtained fluxes and spectral energy distributions for these regions and created line ratio images. So then we combine this with surface brightness data in order to study the role of shock and photoionization in this system. So currently our results have found, so with John Raymond, we've been able to combine this with his shock models to study the roles of shock and photoionization. And we've currently found that both shock heating and photoionization appear to be needed to reproduce the fluxes that we observe. And this work is in prep right now. And as I mentioned earlier, I worked with Margarita, John, and Warren on this. And I think that's about time. And that's also about all I had planned to say. So I'm done. Thank you.
Thanks a lot. Thanks a lot. It feels we had two very interesting seminars here. So let me open for questions.
Yeah, I don't
see at the moment anything written in the chat. You can raise your hand. Oh, there is Randall. Yeah, please go ahead, Randall.
Certainly. Great talk, Carolyn. Are there any other stars besides Myras and Cepheids that we could use for this technique? Is this Myra simply the next in a line of these, or is it basically the end of the line?
Yeah, that's a really good question. And there are other distance indicators we could use, but they all have like, the reason why we chose Myras is because they have a number of unique benefits. So for example, another group of stars that people use for distance indicators a lot is tip of the red giant branch. And they're also very good distance indicators. But the reason why we prefer Myras, which are tip of the asymptotic giant branch in essence, is because Myras are more luminous. So we can see them out to farther distances. And that really is the key when you're trying to get a precise measurement of the Hubble constant, because often we're limited by the number of calibrators that we have, not necessarily by our uncertainties for any one measurement. So we do want to be able to reach as many galaxies as possible. And tip of the red giant branch is up to 2 magnitudes fainter depending on the Myra we're looking at. So that really decreases the volume in which we can search for local type 1a calibrators. And that increases the uncertainty a bit. So there are other stars we could use. Myras in particular, we were interested in for their old age, which allows us to look at all galaxies, and also for their luminosity.
Okay,
yeah.
Thank you.
Thanks. John.
Hi, Carolyn.
Hi, John.
I was wondering whether there is any metallicity dependence in the period luminosity relation for the oxygen-rich Myras, in particular because one of the galaxies you showed, you avoided using Myras near the center of the galaxy. You're looking at the ones far out, and there is a metallicity gradient typically in galaxies from the center to the outskirts.
Yeah, that is also a really good question. So let me go back to, so this is NGC 4258, and the answer is we're not totally sure what the metallicity dependence is for Myras in these galaxies, but so far we haven't detected one. And NGC 4258, we studied the inner region of this galaxy. There were actually 2 fields that they had obtained to look for Cepheids because of potential metallicity concerns, one closer to the center of the galaxy and one further away. And then they tried to calculate the difference in the 0 point from the metallicity. And every time people do this, they always get something slightly different. So we're not sure exactly what that dependence is, and it's probably not a very large one. For Myras, we haven't detected it. So it is something that we do keep in mind, and that is part of the reason why it's probably a little bit safer to use the outer regions of the galaxy, and because that will be a little bit more consistent when we're also looking at elliptical galaxies as well. But yeah, I think we just don't know enough to answer that right now, but the effect also doesn't appear to be very big, because based off of like the gradients that we've just tried to study, even from our own images, like from the center of the galaxy to the outer regions, we don't detect it. And it seems to certainly be smaller than uncertainties that we might have from crowding, which is the primary reason why we excluded that. So it probably does exist to some extent, but it's not the dominant source of uncertainty. So it's not something that has been our main focus on removing at the moment. I hope that answers your question.
Yep, thanks.
Thank you so much, Caroline.
Thank you.
I don't see other raised hands or questions in the chat. So yeah, thanks a lot again. Let's move to the second speaker, and I think it's Pastor Ruth now.
Thanks,
Oh,
Federico.
sorry.
Hi, everybody. Thanks, Caroline, for a great talk. Moving on, we are now going to hear from Jaya Maithil, who is a final year PhD candidate at the University of Wyoming, working with Professor Michael Brotherton. Her thesis research is on the multi-wavelength investigation of the orientation of quasars and the accretion rates of their supermassive black holes. She uses radio, optical, and X-ray data from ground and space-based telescopes for her research. Born and raised in India, she received her bachelor's and master's in physics from the National Institute of Science Education and Research in India. So Jaya, please take it away. And for everybody else, please feel free to put questions in the chat as the talk is going, or you can wait till the end and ask them then.
Thank you, Ritu. Let me share my slides. Okay, so first of all, I would like to thank you for giving me this opportunity to present my research. In today's talk, I will cover two exciting projects from my thesis that investigates X-ray properties of highly accreting quasars and provide some modified prescription of their black hole mass estimates. Highly accreting quasars are characterized by large Eddington ratio. Eddington ratio is the bolometric luminosity divided by the Eddington luminosity, where the Eddington luminosity is the limit where gravity balances the radiation pressure for a spherically accreting object. Highly accreting quasars are not so common at low redshift, but across the cosmic time, their fraction is expected to increase. Observations of billion solar mass black holes at high redshift cannot be explained with Eddington limited accretion. The growth of supermassive black holes in the early universe may require super Eddington accretion rates to accomplish. The accretion disk structure of highly accreting quasars likely differs from the thin disk thought to be present in the low accreting AGNs, and this difference may be diagnostic in X-rays. Also, recent reverberation mapping campaigns are showing that the high accretion rate objects have systematically smaller broadline region radius, which has a huge consequence for the way we estimate the quasar black hole mass. So the key to identify high accretion rate quasars lies in determining their mass most accurately. At low redshift, we can determine black hole mass based on reverberation mapping, assuming that the broadline region clouds are virialized. The full width half maxima or the dispersion of broad emission lines like H beta typically sets the velocity delta V based on the Doppler broadening, while the radius of PLR can be determined by multiplying the speed of light with the time lag between the emission line and continuum determined by the reverberation mapping. Only a few hundred AGNs have reverberation mapped black hole mass so far, but fortunately, an empirical relationship was established between the time lag and the continuum such that the radius of broadline region is proportional to the luminosity to approximately to the power 0.05. Assuming that this relationship holds, single epoch spectra can provide mass estimates. However, the reverberation mapping samples used to establish this RL relationship were biased towards low accretion rate AGNs. More recent reverberation mapping campaigns like the Super Eddington accreting massive black hole campaign and the SDSSRM campaign are showing that the observed radius is significantly shorter than predicted by the traditional RL relationship. The CMBH-RM campaign is set out to examine the radius luminosity relationship of the most highly accreting agents. They selected their targets based on a dimensionless accretion rate parameter m dot given over here, which is derived from the Shakura and Sonia standard thin disk equations. So m dot greater than 3 implies that it is a CMBH. Their results reveal that the highest accretion rate agents have systematically shorter time lags, a factor of 3 to 8 times smaller than predicted by the canonical RL relationship, which is established for the sub-Eddington accreting agents. In fact, their results show a population of extreme objects with log m dot greater than 1.5 that has markedly small BLR sizes. So the X-ray and optical properties of these objects may be diagnostic of the structural change in their accretion disk. So our sample consists of these extreme objects, the extreme CMBHs. There are 13 of them. We use Du and Huang 2019 data for their black hole properties. 5 out of these 13 objects had XMM observations. We obtained new Chandra observations for 8 CMBHs. We also obtained almost simultaneous optical spectra with our Chandra observation. So what gives X-ray and optical UV emission in quasars? So this video shows the basic geometry of accretion disk, although it should have an additional lensing effect that is not illustrated here. But as we know that the accretion disk around the central black hole glows bright in optical UV and soft X-rays. According to the disk corona model, hard X-rays are produced by upscattering of disk photon by hot electrons in the inner part of the nucleus called the corona. Hence, X-rays are probe of accretion and carry direct information on the physics of the inner regions. The X-ray spectrum of 2 keV is dominated by a single power law with a hard photon index close to 2. Therefore, the hard X-ray photon index gives direct information about the energy distribution of the electrons in the corona. The spectral energy distribution of AGNs peak in the UV, which is emitted by the accretion disk. The relative strength of the disk and the corona is shown by the relative strength of the energy emitted by the 2 regions. This is parameterized by the 2-point spectral index, alpha OX, between 2500 angstrom and the 2 keV. So a decade ago, there were suggestions of correlation between hard X-ray photon index and Eddington ratio. Now we have identified these super Eddington objects to test if this correlation extends to them. A high accretion rate is expected to soften or steepen the hard X-ray spectrum by increasing the level of disk emission, but corresponding shift in the energies that result in softer photons overall act as in cooling component cooling of the corona. Also, alpha OX is known to show strong anti-correlation with the optical UV. It is a byproduct of nonlinear relation between luminosity at 2 keV and 2500 angstrom. It implies that optically bright AGNs emit relatively fewer X-rays than the optically faint AGNs. Recently, Castello-Moore looked at the alpha OX as a function of the accretion rate parameter m dot, finding that the most highly accreting sources have steeper power laws, although their result is limited to a small number of statistics. So we test these correlation for our CMBH sample. So here I present the Chandra data of 2 of our targets with energy on the x-axis and the count rate on the y-axis. Figure on the left shows spectra of 1 of 6 objects that shows soft, steep spectra well fitted by a power law with only galactic absorption. And we measure the photon index and the rest frame 2 keV luminosities from the best fit models. 2 of our objects are outliers and have much harder spectra than for a typical CMBH. An example is shown on the right. We fit their spectra by using a power law model again, but with both galactic and an intrinsic absorption. These objects need a more complex model, but their low photon count prevents us from uniquely doing so. So there has been another group, including Hazhen Liu and Bin Lu, who are also working on the X-ray properties of CMBHs, and they published their results earlier this year. There is a little bit of overlap between our sample and their archival data. So in the following plots, I will show our Chandra and XMM CMBHs overplotted over their sub and super Eddington sample. So the figure on the left shows gamma versus the Eddington ratio, whereas the figure on the right plots gamma versus the m dot. Our results establish that observed correlations between hard photon index and accretion rate parameters indeed extend to the extreme CMBHs. The gamma does steepen even more for these extreme accretors. Next, I look at the alpha OX correlation. Figure on the left plots alpha OX versus the 2500 angstrom luminosity. It shows that the CMBHs follow the Stephen et al. 2006 relation pretty well, which is represented by this black dashed line. Figure on the right plots alpha OX versus the dimensionless accretion rate parameter m dot. And we think that there is only a marginal correlation between these two quantities. Recently, Liu et al. 2021 established a new three-dimensional plane between alpha OX Eddington ratio and the black hole mass, which is seen edge on in this figure. So as we can see that this correlation space extends to our extreme CMBHs. So now I'm going to switch gears and move to the second part of the talk, where I will discuss the physical parameters of highly accreting quasars. So as I mentioned earlier, the CMBH RM indicates a BLR size 3 to 8 times smaller than predicted from the traditional RL relationship. And as you can see that mass is directly proportional to the BLR radius. This implies that the black hole masses using the canonical RL relationships are overestimating the black hole mass by the same factor. Du and Huang looked at the offset between the radius of BLR from the RM measurements and the one estimated from the canonical RL relationship, and found that it shows strong anti-correlation with the strength of iron 2, which is the ratio of flux between rest-frame optical and the H beta. RFE is an eigenvector 1 property known to correlate with the accretion rate. Therefore, accretion rate-based corrections to the RL relationships are really crucial. And Du and Huang established a new RL relationship by incorporating the strength of RFE, which is given over here. We use this updated radius luminosity relationship to quantify the overestimation of black hole mass and the underestimation of their accretion rate. So we used all the archival data set possessing a rest frame optical spectra. The table lists the sample we used. The plot shows the radius luminosity space spanned by our quasars. So for the low redshift Shen 2011 quasar catalog, we applied a conservative signal to noise and a redshift cut to select sample unbiased by the poor spectra of H beta region. And we kept most of the targets in the other samples, in the other high redshift samples. So to estimate the single epoch mass, we use the virial equation, which I discussed earlier, which uses the RL relationship to predict the radius of BLR. So from the previous slide, we know that radius in the RL relationship also depends on its spectral properties, primarily the strength of optical iron. So when we use the iron-corrected RL relationship, it gives a black hole mass that are unbiased of the accretion rate effects and hence provide a more accurate estimate for the black hole mass rather than if we use the canonical RL relationship, it doesn't have that correction. So figure on the left shows canonical and the iron-corrected black hole mass in log-log scale, and the samples are indicated by this color code. The canonical mass, again, is the one without the iron correction. So the plot shows that black hole mass is systematically overestimated using the canonical RL relationship. And as the accretion rate is inversely proportional to the black hole mass, the accretion rate is systematically underestimated when using the canonical RL relationship. Now, as canonical and iron-corrected black hole mass differ primarily due to the RFE factor, which is an accretion rate indicator, therefore the plot of the mass ratio that is canonical to the iron-corrected mass against the accretion rate parameter m dot, we see that there is a strong correlation between these two quantities. The high redshift quasars, that is the one that have redshift greater than 1, on average host higher accretion rate black holes. And the iron correction is very important for their mass estimates, which can be seen from the figure on the right. So here again, we plot the mass ratio against the redshift, and we are color coding it by the accretion rate m dot. So we see that the average overestimation of mass increases as the redshift increases. The overestimation is a factor of around 1.4 for quasars with redshift less than 1. It is a factor of around 2 for quasars in the redshift between 1 and 3. And the overestimation is highest, a factor of 3 for quasars above redshift 3. So as I mentioned earlier, that RFE is an accretion rate indicator. So it correlates with Eddington ratio. It is known to correlate with the Eddington ratio. So using an iron-corrected black hole mass improves the correlation between these two quantities. So the left figure demonstrates that the Eddington ratio is underestimated when the canonical black hole mass is used, giving a less significant correlation. Whereas the iron-corrected black hole mass more accurately determines higher Eddington ratio for the strong RFE emitters. And this significantly improves the correlation, as we can see on the figure on the right. Now, looking at the accretion rate and black hole mass for our large sample of quasars, which span a wide range of redshift, we discern that high redshift quasars, which are these 4 samples, on average host higher accretion rate black holes as compared to the low redshift quasars, which includes a large fraction of high mass but low accretion rate objects. We also find that the strongest iron emitting quasars belong to 2 classes. First, the high redshift quasars with rest-frame optical spectra, which given their extremely high luminosities require high accretion rates. And their low redshift analogs, which given their low black hole mass must have higher accretion rate to meet the survey flux limit. The bolometric luminosity versus the black hole mass plane, which is shown on the right, shows that there are no extremely luminous quasars at low redshift, which is this gray points. So there are no extremely luminous quasars at low redshift, as only the low mass objects are actively accreting, whereas at high redshift, it is the most massive systems that are actively accreting. And this phenomena is known as the downsizing. So in conclusion, on average, CMBHs continue to follow the known trends of X-ray properties and accretion rate. The picture here shows the slim accretion disk that likely exists in the case of high accretion rate quasars. The height of the inner accretion disk scales with accretion rate, and maybe this change in the disk structure is responsible for both the X-ray properties and the change in the H-beta emitting gas. The slim disk shields the ionizing extreme ultraviolet and X-ray photons emitted from the central region, resulting in an X-ray weak or absorbed resulting in an X-ray weakness when viewed at a larger inclination angle. The two objects in our CMBH sample that show flatter hard photon index would likely be X-ray weak because they are seen at a larger viewing angle. Also, this puffed up disk structure gives an isotropic radiation that would result in a smaller broadline region size. And if we are using the canonical RL relationship, in that case, we will be overestimating the black hole mass of our quasars. So these kind of disk models should be investigated more in future, and it is an outstanding question concerning the properties of quasars and how the observable properties depends on the accretion rate. So I'll end here. Thank you for your attention.
Thank you very much for a great talk. Do we have questions? Please put them in the chat or raise your hand to ask them yourself. Excuse me. That was my timer to remind you, so you finished early. That's good, that's good. So questions. I see a hand up. Yes, Dan.
Yeah, so basically you're saying that the broadline regions are closer to the source of the variability and therefore give a shorter reverberation time.
Yes.
What if the source of the variability, you're saying it's closer to the supermassive black hole, to the center? So what if the source of the variability was just further away from the center than we think, and would give the same time delay?
So the puffed up disk structure. So what happens is that this puffed up disk structure blocks the broadline. Basically the BLR region moves closer because only the inner regions of the broadline region is photoionized by the central source. So I'm not really sure if the ionizing source itself can move outward, but what I have like Huang et al. Discusses that the source is still concentrated in the center, but the region of the BLR which get photonized is closer to the center, and the one that are at larger inclination angles, they get blocked by the thick disk, which is only the inner region of the accretion disk.
Thank you. Dan, is your hand still up from the previous question, or do you have another one? Oh, okay. Any other questions, either in the chat or hands raised? Well, yes, Anita.
Hi, yes, I have a question about the measurement error on the black hole mass, because this must not be very small compared to the differences in the mass, because you see the overall bias of having overestimated masses at high redshift, but what is the error on the mass and how this contributes to the analysis?
Okay, so the error on the mass, the largest factor that contributes to error on the mass is the effectors, but in our analysis, we are using the same effector for both the canonical and the iron corrected RL relationship. So we are not really looking at the orientation effect here. but we are focusing on the accretion, the contribution from the accretion rate bias. And like we see that that overall for high accretion rate objects, the FE corrected RL relationship gives a smaller black hole mass. So over here, I show the errors, which is like the error in the mean.
Mm-hmm.
So
yeah, this is actually, yeah, this is a good plot. And you also have a difference in the number of sources at lower redshift and higher redshift. So this must somehow contribute to the results in some ways. And the error, I mean, overall error on the mass, yeah.
yeah, but the interesting thing is that at high redshift, we do not see these very low accreting objects. The majority are accreting at a very high accretion rate.
Right, so what would be the luminosity of the source which is at higher redshift and accretes at this, you know, the same rates? Because there is a limit to the visibility of the source. Yeah, you have it here. Yeah,
so
you basically see that there is no sources below, you know, basically 10 to 45.5, which you can detect, right, at high redshift. So there is some limitation there. All right, thank you.
Yeah, so this, so because the optical part of the spectrum falls in the infrared region where we don't really have a lot of measurements, and only the bright sources get selected at higher redshift. So that's why we see more luminous quasars at high redshift, which are also massive and accreting at a higher accretion rate.
Yeah, so you have some selection effect, which may play a role in this overall trends. Yeah, thanks.
Thank you.
All right, thank you. Any other questions? I'm not seeing any others at the moment. Both our speakers do have slots open on their meeting schedule. So if you'd like to discuss further, please go ahead and sign up. Also, given that we still have everybody here, if you'd like to help organize this wonderful seminar, please let us know. This is particularly a good chance for all the people who are new to the CFA to get to meet people and, you know, be visible in the CFA when we can't actually be there in person. And you get to meet a lot of great scientists as you reach out to them to give these talks. So yeah, please let us know if you are interested in helping us organize this. And yeah, thanks everybody for joining us and have a great day. Thanks to both of our speakers also again.
Thanks, everybody.
Thank you.